Thank you. Hi, everyone. I'm a PhD student from the University of New South Wales. So I work on the detection of extrasolar planets using the Doppler methods. So Adam just mentioned that the importance of knowing the star in order to know the planets. I will talk about how much we can do without knowing much about the star. And I'm going to introduce you to these three recipes today. The Gaussian composition, Fourier Transform, and Gaussian processes. To start with, let's have a recap on the Doppler detection of extrasolar planets. So it is the star and the planets orbit around the center of mass, and we detect the star wobbling in the line of sight, and we detect the line shift, the spectrum of the star, and it shifts left and right until to infer the presence of a planet. And this is an example of the first exoplanet orbiting, the main sequence star. And we can see that the amplitude are quite large. It's 50 meters per second. But these days, we are getting down to 1 meter per second precision. And this is when the stellar jitter comes into play. So when I talk about stellar jitter, it means like stellar activity on the stellar surface that breaks the flux imbalance on the star, and so that you have different contributions of redshift and blueshift that would induce the spectral line asymmetry. And if we fit the line center, that will shift the line center even without the planets. So it's simply a stellar effect. We have a few effects from the star, like dark spots, bright features, specular pledges, and flares are just eruptions on the surface. And we have stellar granulation, which is due to convection, also stellar oscillation due to the harmonics. So we can write this observed radial velocity as a sum of the planets, the contribution of the planets, and the jitter from the star. So the motivation is to separate these components, the planets and the star. How do we do that? So let's see. We come up with this robust technique, the Gaussian decomposition. It's basically a base of orthogonal functions, and it's composed of the Amid polynomial and some Gaussian term. So any function can be written as a linear combination of the Gauss-Amid functions. So we think that if we can parameterize the line profile, and then this parameterization would represent how the line deforms, then we might be able to tell how much the line is shifted. But then this is like a dilemma, because in order to parameterize the line profile, we need to define the center, but we don't know the center. If we know the center, we know this V already. So this parameterization AN is actually coupled with the radial velocity shift of V. But we come up with some attempted solution here. So if we parameterize the line profile in the rest frame, so when the line is shifted, this AN would become renewed. And the other method is to parameterize the line profile in the observed frame, which means that the coordinates follows the line profile. So any changes in this AN will represent the intrinsic line deformation. So just keep in mind that in the rest frame, it means the planets and the jitter. In the observed frame, it means changes from the star. So the difference of them would mean the changes from the planets. So I'll ask you a question. So this is just a periodogram or Fourier transform of this coefficient AN. So the peaks would mean the period. Can you tell me what is the period of the orbital period of the planet, and what is the rotation period of the star? Okay. So in fact, I input one planet in the system that is with an orbital period of 40.45 days, that is right here, because the red curve we are observing at the rest frame. So any feature showing in the red would mean that it could be a star, stellar jitter, or it could be a planet. And the blue curve here, that is simply the jitter. So the difference between the red and the blue would mean the presence of a planet. So what it looks like in the real data, this is Wolf 1061, the second closest exoplanetary system known. And we can do the decomposition on the line profile in the rest frame and in the observed frame, and we can see 2 peaks in the red, but no corresponding peaks in the blue. That means that these are the planets, the planetary signals. So in fact, this is quite matching with the literature value with the planet B and C. And please come back to me to this planet D if you want to know more about that. And the second recipe is the Fourier transform. So I'll first introduce you with this translation invariance. So there are 3 ways to understand it. First is to basically do a Fourier series of a function, and you can see that this an and bn, which are the coefficients, and if we shift the line, we would get a new an prime and bn prime, and we can find that this is a constant, which means that the power of each frequency remains the same. The second way to understand it is that if this is just a shift of the line profile by x0, and in the Fourier space, it's just a phase shift. So the amplitude is still the same. Or the third way to understand it is if we shift the line profile, it's simply a phase shift. So all the compositions in different frequencies remains the same. So we can see here, if we do a Fourier transform of the line profile, so if the line is shifted, then it would be still the same in the Fourier space. But if it's due to intrinsic deformation of the line profile, then it would be observable in the Fourier space. And if we do the Gauss-Emmy decomposition for this Fourier transformed line profile, then it would be able to reveal some features in the intrinsic line profile deformation. So this is what we get. I haven't done anything about this yet because it's a conceptual framework. But I'm fascinated about recipe 3, which is the Gaussian process. So how many of you have used Gaussian process? Could you please raise your hand? Okay, great. So we have one expert there. I'm quite new in this field, so probably I'm not the best person to ask. So to start with, normally we fit our data by minimizing the chi-square. We have our model, we have the data yi, this is the error. But what if the model fxi doesn't represent what the data will look like? For example, you don't know much about the data, you don't know what the star behaves. So how are you going to fit the planets without this extra contribution from the star? So if you're using just the planetary Keplerian model in this fxi, then you would be probably fitting other components contributed from the star as well. So Gaussian processes look at this problem in another way. So we have basically we have the parametric modeling of the known. So we know that the planet orbital period, we know that the planet is in a Keplerian orbit. So that's our prior knowledge. And we will also model the unknown with non-parametric modeling. For example, the correlated noise described by a kernel. So when it comes to a star, it rotates and the spots come and go. So these are the noise that is correlated because, well, it occurs at a rotation period of the star. So we have several kinds of kernels. So these are just a few examples. We have the square exponential kernel, which means that if two observations are closer to each other, then they are more correlated. And we have the periodic kernels, which means that if the two observations that are at multiples of a period, then they are more correlated. And of course, we have this quasi-periodic kernel, which is just a multiplication of these two. So this is a simulation. So the orbit data is simulated by adding a Keplerian orbit. So this is what I simulated. And also this stellar jitter model simulated with the SOAP simulator. So we try to see if we can recover this planetary signal by combining these two. So it looks quite mass here. We apply a Keplerian orbit as a model for the planet and also a quasi-periodic kernel for the noise model. And then we maximize the likelihood function. Basically, it's implemented in this Python library by Dan Foreman-McKay. And we use MCMC to run the simulation, and that's what we get. So this is the blue curve are the fits, and these are, well, the diagram already speaks for itself. So we have like these blue lines are the true value, and the center of these contours are recovered value. So it's quite close to the true value, about 1 sigma difference. So this is a great successful Gaussian process, but that's nothing new here. What I want to do is to look at the problem in a pixel by pixel variation. So imagine a line is shifted, and then if you stay at the same pixel, then you will see the pixel variation. So this is, so the blue is the static line, and the dashed line here is just shifted line, and the green dashed dotted line is the residual. And you can see that at different pixels, it's shifted. So the line varies differently, and it's actually proportional to the gradient. So if we look at each pixel and see how it varies, then you can see that it's actually related to how the planet affects the line profile. The pixel variation. So we can see that you can see some common features in these 3 panels corresponding to these 3 pixels. So the common feature would be the planetary signal, and the other feature would be the stellar jitter or just noise. So our aim is to extract the planetary signal from all the pixels, because they share the same planetary signal. And maybe Gaussian processes is one of the ways to tackle this problem, because it's successful in recovering the signals in the time series. But what if we combine all these time series together to recover our planetary signal? So the advantage, I think, is that using radial velocity, we have only like 1 time series. But if we look at the pixel by pixel variation, then we have dozens of time series. So that would probably enhance the chance of recovering the planetary signal. So as a summary, so these are just the 3 recipes I presented. And we can use the first 2 recipes to that we know about the star to use as a prior to inject into the Gaussian processes, because the more we know about our model, the more we know about how the noise behaves, the better we can recover our signal. So in the end, bon appetit.
Thanks, Jenny.